So these two reactions are called the acetoacetic ester synthesis and the malonic ester synthesis. And the best part about these reactions is that they are completely deceptive. So the name is the ester synthesis, right? We are not making an ester. We are starting with an ester. And a lot of people will always be like, oh, Rose told me to do like the easy stuff. So if it's a ester synthesis, I'll pick the ester that's an answer. And I'm like, no, because this is organic chemistry, right? So instead, we have to learn what an acetoacetic ester is. So before we get into the reaction, I'm going to draw something for you down here. So this guy on top has two functional groups, which are what? Ketone and an ester. Cool. So this is the ketone part. This is the ester part. And their relationship to one another, we're going to say is alpha. So they're alpha to one another. I mean, I lied to you. I'm so sorry. Beta. And the reason they're beta is because if you start from the carbonyl on the left, we have alpha beta. And if you start with the carbonyl on the right, this is alpha, this is beta. So we can say their relationship to one another is beta. And then we can say the carbonyl on the left is a ketone. So we're going to say it's a beta keto. And then the functional group on the right is an ester. So we're going to say it's a beta keto ester. I know that's a mouthful. So the beta keto ester is like the class of compounds. So all of these guys that we're going to draw are beta keto ester. The acetic ester is specifically the one that's drawn up here. So he will ask you questions where he's like, what's this compound, right? And one of the answer choices is acetic ester, and the other one is beta keto ester. So this guy is just a beta keto ester. There's no more specific, better word for this. I mean, there is, but not for this class. Whereas specifically this molecule on the right, it is in fact a beta keto ester, but it's also an acetoacetic and the best answer choice would be the most specific. So good question. So this part is an acetic or an acetone, I should say. And then this part is an acetic ester. So even though this reaction is called the acetoacetic ester synthesis, you can use any beta keto ester for this reaction. Yes. Yes. So the name of this reaction is the acetoacetic ester synthesis, but you can use any beta keto ester. So the chains can be any length. So this is kind of like the nomenclature stuff for this section. So any questions about that so far? So I will keep this naming stuff, but I am going to take it to the bottom right here. All right. So this reaction looks really long and complicated. So we are going to break it down. So the first arrow has a set of reagents. Do these look similar from any reaction in this chapter? We break it down. This guy has a negative charge. Anything with a negative charge can be a nucleophile or base. So this guy can be a base. And down here, what is this type of molecule called? We have a carbon chain and a halogen. An alkyl halide. And someone just said it. This first step is an alkylation. Cool. So I'm just going to delete all of this garbage from here. So in this guy, we have 2 alpha positions in respect to these 2 carbonyls. This guy doesn't have a second alpha position because it's an oxygen. So we can say we have alpha 1 and alpha 2. Which alpha position is the more acidic one? The second one. So we're going to steal that hydrogen. And there's actually 2 reasons. So one, it's more substituted, but also it has the effects from both of those carbonyls. So it's like double effective. So when we steal that alpha hydrogen, what are we going to put in its place? A lone pair, cool. So, and a negative charge, yeah. So this guy, come in, and there's like no space. So we end up getting 1H and a negative charge. Cool. So that negative charge is now going to react with the alkyl halide, right? And the pH would look like this. But for the purposes of space, we're just going to keep it as pH, but I just want you to know what that looks like. Say pH, pH2, PR. The negative charge is going to attack right here and kick off this bromine. And what kind of mechanism is this? SN2-like, cool. So that means there are no rearrangements or anything. So at this point, we are done with reaction number 1. And I know this is a lot of drawing, so I'll try to go a little bit slowly. So at this point, we've reached A. And all we've done, going from our starting material to product A, or I should say intermediate A, is we've replaced one of those alpha hydrogens with our alkyl group. Yes. It could be any alkyl halide. The only reason I use this one for both sets of reactions is because that's what he uses in lecture usually. Alrighty, so the second set of reagents, we have NaOH and H2O. So NaOH has a negative charge here. So anything with a negative charge can be a nucleophile or a base. Cool. So in this reaction, we think that it could be a nucleophile instead of a base because there's H2O on the bottom of the arrow, and that looks like it's going to be a catalyst of some sort, right? So the OH has to actually do something. Does this sort of kind of make sense? Okay. So we're going to say this guy is the nucleophile. And we have a nucleophile and we have a leaving group. So what chapter does this look like? 17, and I'll highlight that in case anyone doesn't see it. We have our leaving group, and we have our nucleophile. So in chapter 17, when we have this kind of setup, what are we doing? Substitution. So we're replacing the O, R group, with OH. So we get ta-da. And now we have reached intermediate heat. Yeah, well, we could technically call it either product B or intermediate B for 3 separate reactions, but overall, we want to get this product here. So I don't know if that answered your question. All righty. So up until this point, any questions? Yay. Okay, yes, what's up? Just because we want to add an alkyl group. So it doesn't like help or hinder the reaction or anything. It's just because we want to add some kind of carbon chain. But it wouldn't be specifically this mechanism, if that makes sense. So, what is this thing above the last arrow? Heat, okay. And all right, so heat comes up a couple times in Orgo 1. We might have seen it once in Orgo 2 for Diels-Alder. What does heat usually do? Speeds up a reaction. Cool. Specifically in this chapter, heat is going to trigger a very specific reaction mechanism. Does anyone know what it's called? Starts with a D. Decarboxylation. Cool. All right, so what the heck is a decarboxylation? Well, first things first, we're going to rotate this bond so that the OH is pointing upward. So we're not doing anything right now, like any kind of reaction, we're just rotating a bond. So so everything on this left side stays exactly the same. For you guys. So the only thing that changes is this OH is now pointing up, and this double bond is now pointing down. So is this okay? Does anyone have trouble visualizing what we did? All right. So now the actual decarboxylation part of this. So what can happen when we have a double bonded O and an H right next to each other? They could share the hydrogen, and what do we call that? What kind of bond is that? A hydrogen bond. Cool. So I'm just going to highlight the fact that there's going to be H bonding, and H bonding will be here in green. So we have H bonding and we have heat. So what's going to happen is this double bond is just going to go and steal the hydrogen. That's a bad arrow. And that OH bond breaks and goes back to the OC bond right here. And if we make a double bond there, this carbon has too many bonds. So we're going to break this bond right here. I'm going to do a little X. Those electrons go here. So it's almost like one of those reverse steals all the reactions where we had the arrows in a circle and we're making and breaking bonds. So our products are going to look like this. Our side product is always going to be CO2. We don't really care about it, it's just on the side. And I'm going to move this up so we can see a little bit better, hopefully. Okay. So our other product has, bam. And now we have an H. And we have this alkyl group that we had added. And my mistake, that's not supposed to be a double. This is supposed to be a double. Now we have a single bond, hydrogen. A lot of colors and stuff going on. Let me. So what functional group did we make? The enol, cool. And let me zoom out so you can see this whole thing. So someone asked me a really great question last time, which was, how do we know whether we're going to make the E or Z of this guy? So for this class, it doesn't matter. You can make E or Z. I just like to draw the one that looks prettier. But he's not going to give you both answer choices and make you pick one. Yes. Absolutely. And I'm really glad yes, I'm so glad you asked for that because we actually have a part down here just dedicated to decarboxylation because that tends to be a lot. So the decarboxylation step is going to usually look something like this, where we have a carbonyl, usually a ketone or an aldehyde or something. And then on the other side, we have a carboxylic acid. And I'm actually just going to change this color to make it easier. So the first step of the decarboxylation is just to move this bond around. So the reason we're turning this bond is to put the OH next to the ketone. So we end up getting something like this. And right now I'm not including any of the stuff on the bottom just to make it easier. I'll make this 2 hydrogens. Yeah. So all we're doing is like zooming into the last part of that reaction and kind of doing it over again. So what's going to happen is the O and the H can participate in hydrogen bonding. So what that means is that that hydrogen is being shared between both of those oxygens. So I'm going to say H bonding. But when we have heat, that heat allows this ketone to jump up and steal that hydrogen for itself. So now it's no longer being shared, it's just stealing it, which breaks this bond and moves those electrons here because they have nowhere else to go. So once we do that, this carbon right here is going to have way too many bonds. So the only thing it can do is break this bond right here and move those electrons over. So if we draw the left side like this, right? And we draw an H and an H. Let's see what we changed. So we use this double bond, so we have to get rid of it. And we created a single bond to our hydrogen. And then we created a double bond here. And we erased this bond to form a double bond right. So essentially what we're doing is we're cleaving off this whole side and forming a double bond and an OH. And a kind of way you can remember this is it's a decarboxylation. So we're pretty much getting rid of the carboxylate group. Yes. Yeah, so this right here is CO2. And that's always going to be a byproduct of decarboxylation. And the last part I want to show you here is just the ketone enol tautomerization thing. This is not like a step of the decarboxylation. I just want to remind you that this enol could turn into a ketone. So we're going to go bam. And when we do this reaction, all we're doing is taking this hydrogen and moving it to the alpha carbon. So we get ta-da. Yes. So you're saying like, could this side have other stuff on it? Yes. So that's a really good question. So kind of to recap the whole like naming thing we talked about. So the acetoacetic ester is specifically this molecule, right? But that doesn't mean this reaction can only happen with this molecule. This reaction can happen with any beta ketoester. So we could have anything on either side. Or any R group on either side, I should say. Okay, so let's just that, ta-da. And just because I showed you on the other one, I will draw the tautomerization product here. Yes. So you do need an acid or a base. We can assume that we have water left over in here, and water can catalyze it. So that's a really good point. I know this is a kind of long, complicated reaction, but hopefully we can eventually just break it down and we look at the steps and we say, okay, the first one is an alkylation. So whatever is under this chain, we're adding, or excuse me, whatever is under the arrow, we're adding to the alpha position. And then this one is a nucleophilic acyl substitution, which I forgot to write down. And all we do is change that ester into a carboxylic acid. And then the last step is what people usually actually need to draw out. It's the decarboxylation, where we lose the carboxylic acid on one end and just make an enol. Yes. Yeah. Yes. First of all, don't apologize for questions. I love questions. That's a really good one. So this reaction diagram would have like, those three hills. I don't know off the top of my head which one is the rate determining step, and you wouldn't really be asked about that, but I think it would probably be the decarboxylation. Yes. Okay, yes. So something Dr. West was mentioning in class was that the ketone is more stable than the enol, so equilibrium is going to prefer the ketone version, right? So that's kind of why we drew this product at the end. So your product that you make strictly from this reaction is the enol, right? But what she asked was, can we assume that if there's H2O, we prefer the ketone so much that our answer is always going to be the ketone form? So in reality, you're going to get a mix of both. Technically, in this class, the answer is the enol, but Dr. West will sometimes try to trick you on the exam by not putting the enol form and giving you the ketol form instead, and people get really confused. So that's kind of why I gave it to you. Does that sort of kind of answer the question? Okay. Perfect. Yes. So that's something I want to talk about. We're going to go back down here. So the question was, are we always making a carboxylic acid in the intermediate step? And yes, we are, because in order to do a decarboxylation reaction, you must have at least one carboxylic acid. So we're going to write our little rules for decarboxylation right here. So rule number 1, you must have at least one carboxylic acid. And, I should probably, the first rule should probably be you need 2 carbonyls, one of which has to be a carboxylic acid. And then the last rule is the 2 carbonyls must be beta to each other. These are the 3 requirements to undergo a decarboxylation. Yes. Exactly. So if we had an extra carbon in between here, so for example, like in here, we would not undergo decarboxylation at all. So what if we had this reaction with something that's not a beta keto ester? Technically, we would undergo the first and second step because that doesn't have anything to do with the decarboxylation, but we couldn't do the third step. So we would just say overall no reaction. Question? I think your hand's up. No, okay. Cool. So usually if he goes through the trouble of giving you all 3 of these steps, he's going to give you something that's going to work with it. But he will test you by giving you questions like this. He'll say, which of the following can undergo decarboxylation? D, cool. Why is it D and not A, B, or C? Cool, yes. So this one has a carboxylic acid and they are beta to one another. These guys are way too far apart. These guys are way too close together. This one doesn't have a carboxylic acid. So D would be the correct answer. Yep, always has to be a beta. Okay. So any questions on the acetoacidic ester synthesis? Yes. Cool. Perfect. Could not have said it better myself. So this guy is the malonic ester synthesis, and if you can look at the reagents, or if you can tell from the reagents, I should say, this is exactly the same reaction. The only difference is instead of starting with a beta keto ester, we're starting with a malonic ester. And a malonic ester is when we have two esters that are beta to one another. Okay, that's fine. Yeah, of course. So if we zoom in, let's start with the carbonyl on the left. So if we're looking specifically at the carbonyl on the left, we want to see how far away the one on the right is. So we can say it's alpha, beta. So the second carbonyl is beta to the first one. And then if we start on the right side, again, alpha, beta. So the relationship to the left is beta to the one on the right. All right, so now that we've kind of done it the long way one time, we're going to do this the shortcut way that I want you guys to do on the exam. So let's pretend we've never, let's pretend this is a fresh set of reagents, right? Not exactly the same one we just did. So in the first step, we have a something and a something. So number one, what would that be? Yes, yes, I'm talking on the arrow. What did you say? Too many? No, I'm kidding. Okay, so I did ask for it. That was my bad. So yes, in the first step, we have a base and an alkyl halide, which overall, those two sets of reagents together mean alkylation. And I want you guys to highlight what's actually being added. So it's CH2PH. And then in the second step, we have OH and H2O. So that looks really familiar to chapter 17, which was what kind of reaction? Yes, a nucleophilic acyl substitution. So this guy is being added. Now, the only difference between the last one and this one is we have two esters. So how do we decide which side we're going to substitute? Doesn't matter. Cool. So you're actually going to substitute both of those guys. Yeah. So this one and this one both act as leaving groups. And the third step is heat. Anytime we see heat, we know it's a decarboxylation. Yes. So in reality, you would get a bunch of different products. Like you'd get 25% of just one side, 25% of just the other side, and then like 50% of both of them. But for the purposes of this class, we're going to say no matter if they're symmetrical or not, both sides get removed and replaced. Because he would have to give you like the specific like energies and everything. He's not going to do that. All right, so going from the starting material to product A or intermediate A, we have all we're doing is adding it to the alpha position. And this time, to make it easy for you, there's only one alpha position. Then in the second step, so for this one, we would only have one alpha position because these two guys are oxygens. Previous one, we want the most substituted side, aka the one that's in the middle of two carbonyls, because that's more acidic. So remember, anytime we have a reaction from chapter 18, unless it's LDA, it's always going to the most substituted side. For this one, no, because on the left side, we have 3 hydrogens. On the right side, we only have 2 hydrogens. Okay. Draw this right quick. Okay. So now we have 2 carboxylic acids. Can this undergo a decarboxylation? So I heard a couple no's, but I also heard a couple yeses. So the rule is you need 2 carbonyls, check. You need at least 1 carboxylic acid, check. And they are beta to one another. So even though the answer is going to look weird, technically, it's correct. It follows the rules. So when we undergo decarboxylation, I'm going to try to show you like how I would do it so I don't have to draw out a million steps, and then you guys tell me if that doesn't work for you. So I'm going to pick the carboxylic acid on the right, and we're getting rid of this whole thing. And we know that we end up making a double bond here, and we end up making an OH here. So I just go ahead and draw that. Again, it's a lot of different colors. Ta-da! I know it's ugly. But did everyone kind of sort of follow from when I went to the middle step to the last step? Was that kind of okay? Okay. Cool. So if you see one of these, or I should say, when you see one of these reactions on your exam, I want you to go about it like this. Because I know 2 hours seems like a lot of time, but you do have double the amount of questions. So in reality, it's kind of the same. So if I were you, I would do it this way. And then if I have time at the end, just go back and make sure I drew everything correct. Okay. All right. Yes. Yeah. So you're always going to make CO2 as a byproduct. Correct. Leah, and then I saw someone else's hand, but I don't know whose it was. That's a great question. So you're only doing it once because only these two are beta to one another. So once you get rid of 1 carboxylic acid, there's no way to do that again. And then I actually did forget to show you the ketone form, so I will do that just in case. And this is a little less ugly because we're used to seeing this. So either one of those answers could be correct. Yes. Yes, it could, but we're not going to worry about that. He's not going to do that to you for sure. It could happen, but not in this class. Yes. Mm-hmm. All right. Any other questions? Cool. So someone please remind me, the alkylation part of these two reactions, what kind of mechanism was it? SN2-like. So he could ask you a question like this, which again, I don't know why the formatting got so messed up, but whatever. So which of these halides is predicted to alkylate a malonic ester as the anion in the highest yield? What the heck, right? So all of this is asking you is, in an SN2-like mechanism, what kind of electrophile do we want? So does SN2 want more or less branching and stuff? Less. So this wants less steric hindrance. So we prefer primary, and then secondary, and then tertiary. So which one of these answer choices would be best? A. Yes. Does anyone need this before I scroll up? Yes. Also, I always get paranoid that my emails don't send. Did you guys all get my email on Friday with the like what to study guide and everything? Okay, cool. And then I don't remember if I said it in SI yet, but it was in the email. So no, I definitely did say it in SI, but that's fine. Up night is December 8th. That's going to be a Wednesday. My review session is going to be 3 to 5, and then Katrina's is 5 to 7. I will have an hour of tutoring from 5 to 6, and then Katrina has one from 7 to 8. And then as far as reading days go, I received my schedule, but I cannot remember what it is off the top of my head. So I will send out another email today just reminding you about those hours. Yes. He did. Yeah, he said he's just doing an extra credit thing. So technically, I am scheduled to work on Wednesday. However, I have a feeling that nobody wants to be here until 8 o'clock doing tutoring in person at FAU right before Thanksgiving. So I'm going to move my hours online. And yeah, if you did make an appointment and you can't come, or if you have a reoccurring appointment, please cancel it so you don't get like whatever happens if you have too many appointments canceled. So yeah, I don't know. I completely lost my train of thought. But yes. No, I am going to have SI, but it's going to be online. So I will send you guys the link for it. All right. So if I don't see you guys, have a wonderful long weekend. Enjoy your families. Please stay safe. Thank you.